Okay, so let's continue with our new topic, error types and accuracy. Now, we have seen the computer structures, the physically, and how a code works on a computer. Now, our objective is how a computer evaluates a value, a number. Of course, we are working on the numbers, right? And we do some computations and we try to obtain some results from it for our design, for example, or for our measurement if we are making a signal processing. So of course a computer evaluates a value in an analog manner and it gives us a value. So just imagine like this: we are doing some operation. For example, I'm constantly touching a point. For example, this is my ruler, and I'm constantly touching a point, okay, on the ruler. So it's like this. So this is 40, and each time I press on it. Now the thing is this. Of course, I want to touch the number 40 on the ruler. First thing is how accurate I am, and the second thing is how precise I am on doing it, because as you see there is a scatter. It's not possible for me to touch the same point due to some reasons, because I get tired and so on. Maybe I feel different between the two touches and so on. So there may be several things. It is the same for the computer, more or less the same. Now, this means that there are two things. One is the accuracy and the other is the precision. Now, the point is, I want to constantly touch the same point 40. So, as soon as I'm close to the number 40, I'm accurate. But the point is, I may touch different point, but certainly I may touch the same point several times. So this is precision. I'm precise, but I'm not accurate. So this is the difference between the accuracy and precision. So as you see, let's look at the graph now. That's better. As you see now, there are several points, and I have the target here, right? And as you see, there is a scatter between the points. So the point is this: as soon as there is a scatter, and as the area that the points or the envelope of the points are away from the objective point, you have less accuracy, and moreover, as the points covers a larger area, so you have a larger scatter, you have less precision. Now just imagine that. So I'm looking at the mean, right? So the mean of these points are somewhere here at the center. Now as the accuracy increases, of course there is a scatter, because some points are away from the objective point or target point, let's say, but also there is a point on the target and the mean is, the average is just or very close to the target point. So my accuracy is increasing, but as the points covers a larger area, precision is still lower. There may be another case. In fact, the points might be very close, so I'm constantly touching the same point, but I'm far away from the target point or objective point. So I have a lower accuracy, but higher precision. Better is that you have the scatter is the area of the points is very small, let's say, and also it is very close to the mean, is very close to the objective or target point. So this is what we desire in measurements or in computations generally. So we want high accuracy and high precision, and in fact this is the difference between the accuracy and precision. Okay, now certainly this is what we have in hand, but we want to quantify it. We want to quantify the accuracy and precision, and then we have something called error. Okay, so that is the measure of the accuracy. In fact, there are different definitions of error, so you can use different definitions in your computations. But certainly, first thing is, what is the definition of the error? Of course, we make an approximation by using a computer, right? Okay, so okay, we make an approximation with the computer, and we have a true value. Okay, the target value. The difference between the true value and the approximation gives us the error. So certainly you make an error in a measurement because of the system that you design. We have a tolerance in technical drawings and so forth. Now, first thing is the true error. True error is the true value, the difference between the true value and the approximated value, because we are making approximations. And of course, this is one way of error, but this may falsify you because it may be different when the values are very large. Okay, so just think that you are dealing with numbers at an order of 1 million. And just imagine that you measured the quantity, or you calculated the quantity 900,000, and the difference is 100,000. Yeah, that's possible. Certainly the error is 100,000 in this case, the true error. Just imagine that you have the true value as 100 and you measured, or you approximate the value as 90. Now this time, in this case, true error is 10. It seems to be very low compared to the 100,000. But in fact, it's not, because normally you should look at the error by means of percentage. Now we have a new definition then, true fractional relative error. It is the ratio of the true error to the true value. Now in both cases, when you use the error is the relative fractional error is 10%, but be careful, true error is larger in the first case compared to the second one. So it is very common to use true fractional relative error. Okay, now of course we are doing computations, and certainly we are doing it by means of iterations. And each time we make an approximation, and by using different algorithms or techniques, we try to improve our approximation, which means that you should have series of approximations. Okay, so remember, from the mathematics, you look or you check whether a series is convergent or not, and it is the same here. We want to check whether our series of approximations are convergent or not. Therefore, we use, because you may not have the true value, for example. The problem might be very complicated. You may not have the exact solution of the problem. And then what you do is very simple. You look at, you check the approximated error. You approximate the error, relative error. And then what you do is you calculate the difference between the current approximation and previous approximation, and you divide it with the current approximation, and you multiply it with 100. Again, it is a percentage error, fractional error. And you say that, okay, if the value that you are interested in, the absolute value you are interested in, smaller than a certain threshold, then the solution is convergent. Here also be careful about something. Now, the true error might be negative. True fractional relative error may also be negative. But here we use the absolute value in general in evaluating the error, relative percentage, or fractional relative error. And we say that there has to be a certain threshold, epsilon s, and in general it depends on the number of significant figures that doesn't change. If the number of significant figures are 3 digits after the 0, then you put n3 and you calculate this value and you say that, okay, this is my upper bound for the computation. This is the upper threshold for the calculation for my approximation. If the error doesn't change, if the approximated error is below this value, then it's okay. So then you say that, okay, there is no need to make further iterations, and you stop there, because CPU, there exists something, we want to make the computations as soon as possible, and CPU time is also a restriction in some cases. So okay, sorry. Now let's see how it happens. Okay, now here we see the Taylor series approximation of an exponential function e to the power x, and the Taylor series approximation is 1 plus x squared divided by 2 plus x cubed divided by 3 factorial plus, and it goes like this, and the nth term is x to the power n divided by n factorial. So certainly, so this is the Taylor series approximation around 0. So as you increase the number of terms, you get closer to the e to the power x. And now we are asked to calculate the true and approximate percent relative errors. Of course, when the power is 0.5, this is the value that you have. So it is 1.648721, and it goes like this. And we are asked to calculate the approximate relative error with 3 significant figures. Okay, now this is what is asked to. Now